So a stationary trolley was held, it was held stationary at point X, so we know that the velocity there should be 0, so I'll say V initial, or you can say Vx. Let's just say Vx is equal to 0 meters per second. Okay, then we move on, which is at the top of a frictionless track, XY. So now they are telling you that XY right here, this track is actually frictionless. That's also important. So you go and label that as well. It's frictionless. Okay. Then when the trolley is released, it moves down the track and passes point Y, which is at the bottom of the track. The trolley then enters a rough path XY. So that's also important. What do they mean when they say the patch or the path YZ is rough? What are they trying to tell you there?
It has kinetic frictional force.
It's gonna have kinetic frictional force, so we can just say it's gonna have friction. So it's gonna come to a stop at point Z, which is 5 meters from point Y. The length or the height of track XY is 3 meters. Okay, those two values are also shown in the diagram. Then the first question is the system between XY isolated? Write yes or no and give a reason for that answer. What do we think?
Yes, because it's frictionless.
Okay, so whenever we say something is isolated, it means that there's no friction or there's no external forces as a whole. So we'll say there's no external forces, no external forces. Therefore, if there's any principle that you should use to calculate a value from X to Y, which one do you think you should use? If there's any energy principle that you should use?
If we had to do what?
If you had to calculate, let's say the velocity at point Y, because that's what we should be needing after this.
We're going to use X. Then
Yes, but which principle of energy?
the top and the bottom. EPI plus EKI top equals to EPF plus EKF bottom.
Yes, exactly. So that is called the conservation of mechanical energy. So remember, guys, if you don't have any external forces, that is what should pop up into your head. So the conservation of mechanical energy. Okay, anytime they say there's no friction or you don't see any applied force on the object, then that's what you should do. And the conservation of mechanical energy, I'm sure it's given in the formula sheet as well. It's just EK at the initial point plus EP is equal to EK at the final point plus EP also at the final point. So this means that we have half mv squared at the initial point plus mgh at the initial point equal to half mv squared at the final point plus mgh at the final point. Okay, I'm sure that question is definitely there and we're going to need that value as well to, okay, maybe the question that was asked is just for a reason, but yeah, that's the equation that you should use. This is for only X to Y because there's no friction. This is for X to Y. If we are looking at Y to Z, which energy principle should we look at? Should we use for that?
Y to Z is not gonna be the same because nobody will have the VF for Y. I
Okay,
think it's good.
yes.
I think it work net equals
Rabalo, you can
to changing
also
EK.
give us your idea. Between X and Y, because there's no friction, then we said mechanical energy is conserved, so we can use the conservation of mechanical energy. But what about from Y to Z? Which energy principle should you use?
The work net equals to EK.
Okay, she says work net equal to EK. Change in EK, by the way. This is
Yes.
I'm still looking for the formula sheet. Okay, that's fine. So this is called the work energy theorem, right? Yes. That will work on Y to Z, but you're gonna need something for that. You're gonna need to draw the free body diagram. And please never forget that if you're going to use work energy theorem, just remember that free body diagram is required. Free body diagram. Because in your work net term there, remember work net is given by F net multiplied by delta x, which is just the length that it travels, multiplied by cos theta, but that theta there is just going to be 0 degrees. So I'm more concerned about F net multiplied by change in x. And to find your F net, there's no way you can find F net without free body diagram. So they should take into account also the FG parallel if it was on an incline. But you can see now the one that we're trying to use work energy theorem on is not on an incline, it's just flat. So there's less errors that you can make. But whenever you see an incline, just try to avoid work energy theorem because you can easily make a mistake if you don't draw your free body diagram. Okay, another principle that can work is obviously work done by non-conservative forces because we do have friction. And then this one says the change in kinetic energy plus the change in potential energy. Okay, so you can use either those two every time they say there's friction. When they say there's no friction, the one that you should use, not to say the other ones will not work. I'm just giving you tips for simplicity. When there's no friction, you can use the mechanical energy conservation, which is this one that we just wrote out. Okay. All right. Lisedi, also welcome. We haven't really done much so far, so we can move together. Okay. So yeah, that's the equation that we'll use to solve 3.3 when they want the speed at point y. So let's see. Let's go through these terms and decide which one is 0 and which one is not 0. This one that I underline, half mv squared initial, is it 0 or not 0?
Which one?
Okay, this one that I have underlined, half mv squared initial.
The VI is 0. No. Yes. Emma, wait.
It is 0.
Is it not 0?
It is 0, right? Because there's no initial velocity. Remember, it was held stationary at point x. So that's definitely 0. So you're going to have 0 for that. And then what about the mgh initial? Is that 0?
No.
No.
Yes, that can be 0. So we can substitute the values there. Is equal to half mv squared final. That is not 0 as well, because final speed is what we're looking for. There's definitely a speed at y, and I'll call it that. What about mgh final?
0.
It's 0. Why? Because there's no height at that y position. Then you can just find what your v final or your vy is equal to. Okay, that's fine. Then I want us to move to, okay, they want the free body diagram and they want a definition and also a conservative force. Okay, remember, just go and also revise this. Your conservative forces are your Fg. I think that's the only conservative force that we can ever talk about in this chapter.
Yes, sir.
Yes, good. And the non-conservative forces, they are like your friction, your tension, your applied force. Those kind of forces are non-conservative. Whenever you see those, once again, guys, remember to use this equation right here, work done by non-conservative forces. And then let's say you have two forces that are present. You have the applied force and also friction. What you can do on the work done by non-conservative force term is you can take applied force and minus friction and then multiply that by change in x, or we can just say force applied times change in x minus friction times change in x, and then that takes care of work done by non-conservative forces. On the other side is just change in kinetic energy plus change in potential energy. Okay. Then let's look at the last question quickly. In which direction is the trolley accelerating as it moves along path YZ, right, from Y to Z or from Z to Y, and also give a reason for your choice. What do we think? On the path Y to Z, is it accelerating towards Y or towards Z and Y? Anyone who has an idea?
I say towards Z
Towards Z. Okay, why?
because the direction is towards the Z.
Okay, because the direction is towards the Z. Okay, good reason. And Lubabalo, what do you think?
Y to Z.
Y to Z. Okay, is it because of the direction of motion as well?
Is the direction of motion.
Okay. Lutabo, do you have an idea on this? I know it was a question.
No, I said towards it because my free body diagram on 3.4,
Yes.
my to the right. So meaning what my acceleration will be to the left. If you get what I mean.
Okay. All right. What if I say that is wrong? Everyone is wrong in this case.
Yeah, that's why. That's my question.
Because, yeah, look at this. Motion and acceleration are not or cannot always be related. Like if, for example, I don't know if we can have a practical thought about this, but just remember this. When you're slowing down, there's these two terms that I'll write for you. There's speeding up. Let's say you're driving. In that case, we say that you are accelerating, and this means that the forces that are making you go forward are larger. But when you're slowing down, and remember that object along path Y to Z, it is slowing down, we say that you are decelerating. I'm not sure if that's the first time you hear that word. No, okay. So accelerating means that you have a positive acceleration. Decelerating means that you have a negative acceleration. And then look at this now. You can have a car or an object that is going this way in terms of velocity. And the acceleration is also going in that direction. But you can also have a case whereby this object is going this way in terms of velocity, but acceleration is going in the opposite direction. Just remember that part. So to answer this question, because we are slowing down, it means we have a negative acceleration, and then we can say that acceleration is going from Z to Y. In other words, it's going towards the right from Z to Y. And then to give a reason for that is because...
Say,
Yes?
can I give my understanding based on what you said?
Oh, yes, go ahead.
Say from 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 X to Y, it was moving fast.
Yes.
It was moving fast. Then when it got to Y to Z, it started slowing down.
Yes.
That's why we say that the acceleration is from Z to Y.
Exactly correct. And then what would be your reason, like in the test?
Okay, okay, it's from Z to Y because I don't know what I'm going to say. I was just gonna be creative in the test.
Yeah, you should always be creative. That's a good idea. If ever you don't know a reason, because I also when I go to the test, like I don't know the reasons for most of these things, but I'll just be creative. Okay, Luolo says negative acceleration. Yeah, that's good, but I don't think that reason will actually pass in this case. But what you can say, you can remember Newton's second law. He says that an object will accelerate in the direction of the net force. So what you can say here is that the net force is towards or from x to z to I'll just say towards y due to the only force being friction. I don't know if you see it now. Because if you draw the free body diagram of this thing now, it's gonna look like this. It's gonna be normal, obviously. There's gonna be Fg, obviously. But there's another force now called friction, which is opposing the motion. So now your F net equal to ma is only going to have friction there, which is a negative force. This is what makes acceleration to be negative. All right, T.S. Luabalo, you have a question?
I wanted to ask if like you could just say like opposite forces acting on the object.
Can you repeat that again? I think my volume today is not good.
Like opposite forces acting on the object.
Yes, you can definitely say that. I think if you mention that the force opposing is friction, that will be good enough. Or if you can also mention that the net force, which is made up of friction again. So those two words, and it's what you should say. And you can even quote Newton's second law, which says F net will be in the direction of acceleration, and the F net is made up of only friction, which is going in the opposite direction. That will be good enough. Okay, but it's a good question, and it's good that we actually cleared a confusion there. All right, just remember that acceleration does not always need to be in the same direction as velocity. If I do this, if you see where I'm writing now, I can say acceleration, which is change in velocity over change in time. In this case, you can see that the final velocity is 0, while the initial is this value that we can find here. Let's say it's 5, divided by some change in time, maybe 2. You can see that the answer is negative, which means acceleration is definitely going in the opposite direction as motion. Okay, but I think that now makes sense to everyone. Then let's quickly look at this one. Maybe we'll see the same kind of principles. It says a 20 kg block is released from rest. Once again, that's a keyword. This means the velocity at A is 0 meters per second. From the top of a ramp at A, at a construction site as shown in the diagram below, the ramp is inclined at an angle of 30 degrees. So we have an angle of inclination to the horizontal, and it's at the top of a height of 5 meters above the ground. First question is always going to be a definition. Oh, by the way, this is, did they say anything about friction? I didn't read anything about friction, but maybe they'll mention it somewhere along the way. But I can see they show the path as being rough there. So yeah, just also those things should guide you as well. But let's move on. The conservation of mechanical energy. Who remembers this definition in words? Yes, Lisedi.
The total linear the total linear mechanical energy in an isolated system remains constant.
Yep, that's good. That is correct. So the total linear mechanical energy in an isolated system remains constant or is conserved. As long as you have the keywords there, you're good. All right. 7.2, the kinetic frictional force between 20 kg and the surface of the ramp is 30 Newton. Now they do tell us that there is friction. So once again, whenever you see a work, energy and power question with friction, then you should remember that you can use, if it's on a ramp, once again, on a ramp, I'll suggest that you use work done by non-conservative forces. You can never go wrong with that one. If it's on a surface, if it's on a flat plane, then you can use the work net equals to change in kinetic energy. But this will always be a good advice for you. Okay. Use energy principles. Once again, they don't specify which one they want you to use, so you can use any that is good for you. To calculate the work done by the kinetic frictional force on the block. Okay, the work done by the kinetic frictional force for 3 marks. You go and write the formula for work done. Work done says that work is equal to the force in question multiplied by change in x multiplied by the cosine of theta, with theta just being the component of the force or the angle between the displacement and the force. Yeah, let me put it that way. Then this is the equation, how it is from the formula sheet. Then you can go ahead and now write it the way you want it. I can say the work done by frictional force is equal to the magnitude of this frictional force. Change in x, I can put whatever I want. I can keep it as change in x too, so that's fine. And then cos, what will be the angle of theta? What will be the magnitude of theta in this case?
$180.
It's gonna be 180. The reason is because frictional force always opposes motion. So in other words, even if you are on a ramp, look at what I do here. Even if you are on a ramp and you are moving this way, your velocity is going that way, frictional force is going this way, there's no other force there that is applied, so you'll agree that acceleration is pointing in the opposite direction. But the point I'm trying to make is that if you're going down, this means that your change in displacement is going to be facing down. So this is your 0 degrees angle, this is your 90 degrees angle, this side is your 180 degrees angle, and then on this side is your 270 degrees angle, in the sake of work done by any force. Okay, so that's why friction is 180, because it's facing in the opposite direction to which the box is actually going. Okay. Remember, you have these recordings as well. Now I figured out why my laptop was switching off, so now it's no longer going to switch off in the middle of the lesson. So you are guaranteed maybe to get the recordings. FK is given in this case, so they were nice enough to give it. Do revise how to find FK from this equation if it's not given. See, it's a function of the normal force, and to find that normal force, you remember, you should always solve for the forces that are going in the y direction to be 0. That's the only way you find the normal force. You don't go and say the normal force is equal to Fg, or the normal force is equal to Fg parallel. perpendicular, without actually solving for all the forces that are in the y direction. It's easy to make that mistake. Okay. All right. Just make sure that you do that, and then you do a complete free body diagram to analyze all the forces that are applied. Okay. There's plenty of videos on this under Newton's second law. Okay. Then we just substitute. Yes, Lubabalo.
Wait, so we can say Fn equals to Fg.
Fn equals to Fg. Yeah, this one we can't say Fn is equal to Fg like that. We have to solve for the forces that are going in the y direction to be 0. All the forces, you can say F net in the y is equal to 0. Because if you say that, it means you're guessing, and unfortunately that's what some of the teachers say, and it's completely wrong. We can't say Fn equals to Fg. We have to draw a free body diagram. In this case, for example, if I do a quick free body diagram, I'm going to have the normal force pointing in that direction due to the ramp. I'm going to have the frictional force going back. I'm going to have Fg going straight down, but I can find the components of that, which are going to be Fg perpendicular and Fg parallel. Then I can remove the main Fg. So when I do F net in the y direction is equal to 0, then I'm just going to have these two forces that are in the y direction, and that's normal minus Fg parallel is 0. I keep on saying parallel, I mean perpendicular. So this means that in this case, only in this case, normal force is equal to Fg perpendicular. Yes, Lisedi, you have a question? Also, Lubabalo. We'll go Lisedi first.
I wanted to say to Lubabalo that Fg is not always equal to Fn. They could put a box with that has an applied force with an angle.
Yes.
Then your Fn now is no more equal to Fg. It's not always equal.
Very good tip there. Yeah. Yes. Lubabalo.
Okay, so in this instance, no, you're saying that we have to solve it first to show that Fn is going to be equal to Fg perpendicular.
Yes, in this case, yes. But you see, they can have a force, just like Lisedi said, that is applied at an angle again on that. That's why you can never go wrong if you do this. Because that case now, you're going to see that there's a force that actually works with normal force. Like that. It's not updating yet. I'm not sure if my network is down. But let's see. Okay. Maybe on your side it shows. Yeah, there we go. Then in that case, if you have that force, then the normal force will be expressed as Fg perpendicular minus this component of the applied force that is at an angle. I'll just call it Fy. So you can see normal force can actually destroy a lot of things on Newton's second law, as well as work energy and power. So just be careful with that. Okay, so anyone who has a calculator can just tell us the answer for this in case we're going to need it for another question. It's work done by frictional force equal to 30 multiplied by the change in x in this case, or it's not really given. So we have to calculate it. And the cosine of 180 degrees. How do we find change in x? Remember, change in x is the actual displacement of the boxes. Is the length of the ramp in this case. How do we find that?
Can we assume that there it's 90, then we say opposite over hypotenuse?
Exactly, and it is 90 because remember we are measuring a length that is vertical. That is always the case. So even if they didn't really show that it's 90, you are more than safe to say that it is 90. Then we can use trig ratios. Yes, Lubabalo, you can go ahead and ask.
No, I wanted to ask if like we can use the motion function.
We can use
The motion function.
the motion. I'm not sure I can hear you well.
The motion function, don't like what I say.
Or the motion equations. Oh yes, yes. We could use motion equations. That would definitely work. But in this case, we don't have. Do we have enough information? We might have enough information, but yeah, that's gonna take a while. Or yeah, it's a long method to do that, but it's definitely can work. But remember, I don't think we have enough information. We don't have acceleration as well there. And we can't say it's 9.8 meters per second. So if ever you're using motion equations on work, energy, and power, remember that acceleration is no longer going to be the one for vertical projectile. Makes sense, right?
Yes.
Yes, just be careful with that. It's very, very important. But trig can work definitely very well. And I think if I just divide 5 by sine 30, I'm just going to get 10 meters. Just check with me.
Yeah.
Okay.
It is like
Yes, then that means the work done by friction will then be negative 300 joules. And someone can ask, do I write it as a positive? What do we say?
it doesn't matter because frictional force is not a vector, it's a scalar.
Okay, Luabalo said as a positive. Work, it's work. That is actually a scalar. So every time you solve for work, you don't change the sign. It's gonna be lived as a negative like that, simply because it's a scalar. A scalar doesn't have direction, right? So negative 300 joules, that's the final answer. Okay. All right. Then you get 3 marks for that. So they'll mark either of your equation, they'll mark your substitution, and also your final answer.
Say,
Yes.
say, doesn't a scalar always doesn't have a negative because what's that? The scalar only represents magnitude, and I forgot what it is. Nay,
Yeah.
I know that a vector has a negative. A vector is, for example, displacement has a negative, and yeah, see.
Okay. Yeah, I understand what you mean. Okay, I understand what you mean. Yeah, magnitude can also be negative, if I should answer that one. But a vector, remember, a vector can have positive and negative. When it's negative, you can change it and change the direction. But a scalar, like work in this case, it's different to time and mass. You see, when you talk of time and mass, you can never have a negative. If you have a negative, then you did a mistake. But in the case of energy, work, you can have negative work or negative energy. The meaning of that is that the energy is being taken out, or the work is being done out of the object or in the other things, out of the object. But you can definitely leave those ones as negatives. Let's just say for work and energy. But for these other scalars, if you have a negative, it just means it's wrong. It just means you made a mistake. You can never have a negative time or mass, if you know what I mean. But yeah, that's a good comment or question. That's good. Okay. This was 7.2.1. Let's look at 7.2.2. The speed of the block at point B at the bottom of the ramp So energy principle to be used, it's on a ramp, there's friction, it's work done by non-conservative forces, and you have to be careful of how many non-conservative forces you have. In this case, it's just one, which is friction. So we already even calculated that value. So we can just go ahead and write out the equation mgh in final minus mgh initial. One thing I also want to mention, see, when it comes to this, you can be easily tempted to do this. Please avoid doing that. Avoid doing that. Just write out the final term minus the initial term, just to avoid mistakes, because this is wrong. The correct version is this, but just avoid doing that overall. Okay, just write out everything nicely like that, then you can never make a mistake. So if we substitute the work done by non-conservative forces, once again, there's only friction present. So I can just change it and say work done by frictional force. And it's negative as well. So you substitute that as a negative value, negative 300 is equal to, then we'll just leave or write zeros for the terms that are zeros. Final speed will not be 0. So I'm going to keep that 1/2. The mass is 20. V final, I'll call it VB squared, minus initial speed is 0, so that term falls away, plus half mgh final height is 0, right? So that falls away, minus mgh initial, this initial height, so 29.8 into 5. If you have a question, please ask before we move on. Then anyone with a calculator can help us. And if you're doing everything correctly, you see this term is negative. So it means when I bring back this one to the other side, I should have overall a positive answer on that other side. So this one should be larger than 300 if you're doing everything correctly. If you get a negative on the other side, then that means there is a problem. So at the end of the day, it's going to be, I'm getting 980, a positive 980 when I take it to the other side, then minus 300 from that. We get 680 is equal to half of 20 is just 10 v squared, and if I divide by 10 I get 68 equals to v squared. Then what is the square root of 68? Help me out, guys.
Oh, sorry, 8.25. I was muted.
Oh,
Sorry.
8.25.
Yes.
Okay, 8.25. So look at what I'll do. I'll avoid these things that I wrote in blue and just go ahead and write the final answer for that. There's no, you don't lose any mark for that, and you save yourself from making mistakes. But if you think you're not comfortable with doing that, you can write everything or every step. But once again, it opens up a room for mistakes. And that's it. You don't need the direction. It's a vector, but you don't need the direction. That's why we refer to it as just being speed, because you don't really need direction for that. We know that it's flowing down the ramp. It's going to get faster and faster, even though there is friction, but yeah, it's going to be down the ramp. Okay. So let's look at the last question for this 7.3. It says 7.3, a 100 kg object is being pulled up the same ramp at a constant speed. Okay. Work energy and power. Every time I see constant speed in like the last question of the problem, I know they'll want me to find the average power, because average power equation, if you look at the formula sheet, the equation for average power says that this is the force in question, not the F net, just the force that is making the pulling, multiplied by the V average. And this V average is the constant velocity or the average velocity. So you can have two cases here. If V is constant, so that is just equal to V. Or if there's initial and final speed, let's say there's initial and final speed, V initial and V final, then for average, you know that you should just take initial, add the final, divide by 2. Okay, if I was quick, just raise up your hand and ask me to repeat, then I'll repeat, because I'm saying this for the sake of if you find a question that actually wants you to think of it in a different manner than that. Okay. Let me wait, where is that thing? See, now this thing is a little bit confusing now because it's an update, but anyways, I think it could be here. Oh yes. Okay, then the kinetic frictional force between the 100 kg block and the surface of the ramp is 25. Calculate the average power delivered by the small motor in the pulling of the object up the incline. Okay, good question. We need a free body diagram to be able to solve this. They say it's the same incline, right? So the same incline of 30 degrees. Pay attention to what I'll do. Then you will have a motor at the end of this incline. I'll just draw something that looks like a motor, I guess. So this motor is pulling an object with a constant velocity, 100 kg, constant velocity of 2 meters per second. And they also give you friction. There's also friction. The value of friction was given as well, 25 newtons. Okay, here's the thing. When you are finding the average power, or power in that case, that is being delivered by the motor, you are looking for this force, only this force that the motor is using to pull the object up the incline. So how do we find that force? That is the actual question. How do we find this force that I highlighted? I'll just call it force of motor, F motor. We do the free body diagram and we solve for the F net equal to MA. But in this case, A is 0 because it's constant speed. So you see how the dots are going to connect in that case. So let's do exactly that. I have to move this away a little bit. So the free body diagram will look like this. Don't be lazy to draw the free body diagrams every time there's a need, because they are the only way you can analyze anything in physics. I'll call this FK. And remember, you have FG as well. FG going straight down, and you have normal force. Normal force. And this FG has to be broken into components. Oops, what happened there? You have the FG perpendicular component. You have the FG parallel component. Then I can just get rid of the FG when I have the components like that. So I'm still looking for F motor, because in my equation for power, I have to put F motor in there. Let me actually indicate that as well in my equation here on top. I have to write F motor, not FG or F anything else. It should be F for the motor, because the power itself is being provided by the motor. Okay, so I'll say F net is equal to MA, but because of constant acceleration, A is 0, making F net equal to 0. Therefore, I have F motor, and then I'll just subtract these other ones because they are going in the negative direction. FG parallel is equal to 0. Therefore, I can see that my F motor is going to be, take these other boys to the other side, we get 25 for normal force. We get this guy is simply mg sine theta, right? So plus m is 100, g is 9,8, sine theta, our theta is 30 degrees. So what do we find for F motor?
We get 515.
515, is there any comma?
No.
Okay, 515 Newton, and that's the thing, that's the one that we need to substitute in the power average. The question, by the way, is calculate the average power delivered by the small motor up the incline. So average power is equal to F motor. For that, our F motor is 515. Our V average, they gave us a constant velocity, so we're just gonna put 2. Then what do we get?
1030.
1030, 1030. The units?
W watts.
Watts. Okay, there we go. Any question on this one?
No.
Anyone who maybe learnt a new thing on the power on the 7.3 alone? Anything that you didn't know up to this point?
It was the F part that we have to only use. Yeah, we have to only use the applied force.
Yes, the F, only the force in question. You can get a lot of scenarios, but remember, the one that you're interested in is only the one that is doing the actual pulling. They'll mostly give you constant velocity if they want you to first find the force. So I think the max distribution here will be 2 marks for finding the force, and then 2 marks for finding the answer. I think it could have easily been 5 marks, but it's 4 in this case. Okay. All right, then I'll save this recording